Divergence theorem. Let S be a piecewise smooth closed surface and encloses solid E in space. Assume that S is oriented outward and let F be a vector field with continuous partial derivatives on an open region containing E. Then the triple integral of E div F dv equals the double integral of f dot ds over the surface S. So the big deal here is when I think of the idea of the divergence theorem, if I'm going to use a double integral here, my double integral has to encapsulate the whole volume. So what I mean by that is if I was looking at this volume to look at the flux, the outward flux on this volume here, I would need 6 different integrals because each side is going to give me an integral. So there's 3 there, and there's also 1 there and 1 away in the back and 1 on the bottom there. So altogether that would give me 6 integrals. So that's why to try to do this in terms of the double integral is inefficient when I'm dealing with the divergence theorem in volumes. Unless those volumes are completely encapsulated like a sphere. A sphere would cover the whole volume if I was talking about inside of a sphere. Other than that, if I have other shapes, it gets to be quite involved if I want to do it in terms of the double integral. So this is the power of the divergence theorem, is I can just look at the volume of it and be able to calculate the flux through the volume. And notice what it says here. The divergence theorem relates to a flux integral across a closed surface to a triple integral over a solid E enclosed by the surface. So that's what we're dealing with here. So let's have some fun with one of these divergence theorem integrals. So here we go. It says, for the following exercises, use a computer algebraic system and the divergence theorem to evaluate the surface integral of f dot nds for the given choice of f and the boundary surface S. For each closed surface, assume n is the outward unit normal vector. So 379 says, let f xyz equal xi plus yj plus zk. S is the surface of the paraboloid, z equals x squared plus y squared for z between 0 and 9. Okay, so what we're going to do here is we're just going to do the divergence theorem here. So I'm just going to write it out. And we can use either side here. So I'm going to use the left side here. I'm just going to do the volume of this shape. I think it'll be much nicer than trying to do the surface areas to get the double integral. And I'll show you what that means in a second. So when I look at the shape here, notice what's going on here. This is my paraboloid here, where z equals x squared plus y squared. And that's the surface it's talking about here. And it goes up to 9. So what I was getting at is if I'm going to do the triple integral, all I have to do is calculate this volume all together here. Now if I'm going to use the double integral here, I'm going to have to do the whole outside, and that's going to give me all this. And then I also have to do the top of it to enclose the whole volume there. So that would be 2 integrals I would have to do here in order to get that answer. So that's the idea of what we're dealing with here. So I'd prefer to deal with the triple integral just because the volume is going to be a lot easier. And this z equals 9 is just going to be a bound for my z. And I'm going to use here cylindrical coordinates, and I think that's probably the best way to go with this problem. So I'm going to do the triple integral and using cylindrical coordinates. So I'll need the div of f first, and that's very quick to compute. So the div of f is just the partials as they go in order. So px, which is 1, plus qy, which is 1, plus rz, which is 1. So that turns out to be 3. That's the div of f. That's it. Just the partials in which they go, x, y, z, and then I add them together. So that's my div of f. It's 3. So now setting up the triple integral now, it just becomes the volume problem. So that's going to be a 3 there. So let's talk about upper and lower bounds, because we have to put an R here, because remember we're doing cylindrical, so we have our Jacobian, and then dz, dr, d theta. So if I just look at my z here, the lower bound for z is going to be this function here, that surface, and that's going to be this paraboloid. And I have to turn it into polar as well. So really what that bottom function is z equals r squared, because x squared plus y squared equals r squared. So my lower bound for this is going to be r squared. And my upper bound, it says my z goes up to 9. So we're going to put our 9 here. So now for the next bound, that's my r. How far does my r go out? Well, I know here that my z gets as large as 9. So 9 equals x squared plus y squared when I think of the equation here, up here at 9 here. So that's going to be r squared equals 9, which means r equals 3. So that goes from 0 to 3. And then my theta goes from 0 to 2 pi, because it's just going to go all the way around. So there's our setup for our integral. And then once we punch that in, we get for an answer 243 pi over 2. So there's our answer for this divergence theorem problem. Just remember, if I'm going to use a volume like cylindrical or spherical coordinates, don't forget the Jacobian. That's the big thing there. And honestly, drawing the picture is nice because it helps me with the upper and lower bounds. All right, there's our answer.